Next up, we're going to take a look at a couple of examples that really ought to be done using the technique of cylindrical shells, and we'll explain why as we're working through the problems. So first off, we're going to determine the volume of revolution when the region, bounded by y equals 6x squared minus x cubed in the x-axis, is rotated about the y-axis. Now, good first step in any of these processes is to actually figure out what the region looks like. 6x squared minus x cubed is going to have a root of multiplicity 2 at the origin, and we're going to see an x-intercept at 6 as well. Should go up in this direction and then down in this direction. So the region in question would be this region right here. What we're going to do is draw in a sample rectangle. Sample rectangle, when you have y as a function of x, will be in this orientation, and we're going to be rotating this about the y-axis. As such, as you can tell here, we are going to be sweeping out a cylindrical shell. Now for a cylindrical shell, that means that we are going to be finding volume as the following formula. This is the circumference times the height times the thickness. Now what we're going to do over here is identify all of those variables. We start by conjuring Thor. The thickness of the cylindrical shell is going to be determined by this little tiny change in x right here. That will be the thickness of the cylindrical shell. Because it's a little tiny change in x, it'll be dx. As such, when we find our height and our radius, those will need to be in terms of x as well. The height of the cylindrical shell is this dimension that we see right here. That'll be the height. Now you'll notice that in this case, the height is going to be a vertical variable being y. Now with the fact that it's y, however, we're going to make a substitution on that to get it in terms of x. This will be 6x squared minus x cubed. The radius is the distance from the axis of rotation out to our sample rectangle. That would be this distance right here. Now you'll notice that this is simply a horizontal distance from the y-axis over to our sample rectangle. A horizontal distance is simply going to be an x variable, or more specifically, if we wanted to do right minus left, this would be x minus 0. So there we go. Next up, we turn this into Chet. Now the bounds on this we sort of already figured out due to the fact that the x-intercepts are going to be at 0 and 6. So 0 and 6. Circumference is 2 times pi times a radius. The radius in this case is going to be the x variable. The height is going to be our 6x squared minus x cubed, and our thickness is going to be dx. And that would be how we set up our integral to represent the volume of revolution. Proceeding to evaluate the integral, we'll take the 2 pi and factor it outside of the integral, like so. The x I'm then going to distribute through to the two terms inside the parentheses. That'll give us 6x cubed minus x to the 4th dx. In this form, we are ready to integrate, so let's go ahead and do so. Applying the power rule to both of these terms, the power of x goes up by 1, and we divide by the new power. This will be x to the 4th over 4, and 6 over 4 reduces down to 3 over 2. For x to the 4th power, this will become 1/5 x to the 5th power, going from lower bound 0 to upper bound 6. Plugging these bounds in, this will give us 2 pi times 3/2 of 6 raised to the 4th power minus 1/5 of 6 raised to the 5th power minus, when we plug in our lower bound of 0, we are going to wind up with a lot of 0. Now, as fun as it looks to try to, do this one by hand, I think I will turn to the calculator to help me out. So we'll start by doing 3 over 2 times 6 raised to the 4th power minus 1 over 5 times 6 raised to the 5th power. I see that we wind up getting a decimal, which we can turn into a fraction by pressing math, enter, enter. I would like to point out, though, that this is just these two terms right here, and that we're still going to multiply this by 2 pi. Now, the pi will just remain separate, but we'll go ahead and multiply by 2 to make sure that we have that part. That is going to wind up being 3,888 pi over 5 for a final answer for our volume. Neat. Well, that one didn't seem too complicated, so I guess we better make it more complicated. So here's a more complicated example. When the axis of revolution is not simply one of our two axes, the x-axis or the y-axis. So I'd like to determine the volume of revolution when the region bounded by x equals y squared and x equals 4y minus y squared is rotated about y equals negative 3. Once again, first thing I'd like to do is sketch the region in question. X equals y squared is going to be a standard parabola opening to the right, like so, symmetric about the x-axis. X equals 4y minus y squared. If we were to factor this, we could factor out the greatest common factor of y and a 4 minus y. The fact that it's minus y squared means the parabola is going to be opening to the left, and we will see y-intercepts at 0 and 4. As such, we are going to see something that looks approximately like this. So the region in question is going to be this little region right here. Additionally, we go down 3 units to right about here, and this is going to be our axis of rotation this time. Now, because we have x as a function of y, that means the orientation of our sample rectangles is going to look like this. We are going to see a right minus left motif for these. Now, when we rotate this about this line, hopefully it is fairly obvious that we are once again going to wind up with cylindrical shells. So with all of those things in mind, the volume is going to be equal to the definite integral from a to b of circumference times height times thickness. And the way that we determine these things is we start with Thor. Now, as far as thickness of the cylindrical shell is concerned, this time the thickness is going to be just a little tiny change in the y variable as indicated by the picture here. As such, we're going to see dy. The height of our cylindrical shell is going to be the distance from the top to the bottom of the rectangle, or in this case, the right side to the left side. As such, we're essentially going to see what will be an x2 minus x1 in this sense. So x2 minus x1. You'll notice that the x2 in this case is the parabola that's opening to the left. That was this parabola here, 4y minus y squared. So 4y minus y squared minus x2. No, sorry, x1. x1 is the parabola opening to the right in this case, which was our x equals y squared. And that'll be something that we can simplify to 4y minus 2y squared. Just barely fit it in there. The radius is going to be the distance from the axis of rotation to the sample rectangle in question. Now, the way that we're going to put this together is that the distance from the x-axis up to this sample rectangle would simply be a y variable. Additionally, the distance from the x-axis down to this line would be an additional 3 units due to the fact that this is y equals negative 3, and the distance from 0 to negative 3 would be 3 units. As such, our radius is going to be the sum of these two distances. We'll see a radius of y plus 3. The alternative way to think about this is that if you're doing a change in y like this, you should see the top y minus the bottom y. So y minus negative 3, which will give you the same y plus 3 as what we see here. Now, as far as bounds are concerned, we would want to figure out the 2 points of intersection for this. So if we were to set y squared equal to 4y minus y squared, add y squared and subtract 4y from both sides, and then factor as much as possible, we would be able to see that our 2 bounds on this are going to be y equals 0 and y equals 2. This time we're not going from intercept to intercept due to the fact that we have 2 functions and they have points of intersection. As such, we are going to see the definite integral from 0 to 2. Circumference is going to be 2 times pi times the radius, which is y plus 3, times the height, which we calculated to be 4y minus 2y squared, times the thickness, which is dy. This would be the setup of the definite integral that we are going to be evaluating. Now from here, to actually evaluate this thing, we're going to factor out the 2 pi, and we are going to expand what we see inside the parentheses here. I'm also going to list it in descending order, just for personal preference. So highest power of y that we're going to see is going to be negative 2y squared times y. That'll be negative 2y cubed. As far as a y squared term is concerned, we'll see plus 4 from the first term, and then minus 6 from the last term. Plus 4 minus 6 is going to be minus 2 times y squared. And then as far as a y term is concerned, that'll come from the inner term of 4y times positive 3. Now that we've expanded, next thing for us to do is going to be to actually evaluate. We'll be using the power rule for this. I think everything got done there. Yeah, I think that's good. All right, so power of y goes up, and we divide by the new power. Y to the 4th over 4 multiplied by negative 2 will give us a negative 1/2. For the next term, we'll see minus 2/3 y cubed. And finally, plus 6y squared down at the end. This will be going from 0 to 2. Plugging in these bounds, looks like we might want to make use of the calculator one more time. Negative 1/2 of 2 raised to the 4th power minus 2/3 times 2 raised to the 3rd power plus 6 times 2 squared. And plugging in the lower bound of 0 is going to give us trademark a lot of 0. So I think at this point, turning our energies to the graphing calculator will probably save us quite a bit of work. So negative 1/2 times 2 raised to the power of 4 minus 2/3 times 2 raised to the power of 3 plus 6 times 2 squared. We see that this will give us 32/3, which we are then going to multiply by 2 pi. This one I feel like I can handle without the calculator. 32/3 multiplied by 2 pi is going to give us a final answer of 64 pi over 3. That'll be our final answer for this volume of revolution using cylindrical shells.